All right, let's get started. My name is Adrian Fagin, and I want to welcome you to our quantum matter seminar. The dynamics is going to be very simple. Our speaker is going to talk for about 50 minutes or so, and everyone is going to be muted. And at the end of the talk, you can raise your hand or post questions on the chat box, and we're going to allow you to ask directly to the speaker, or we're going to read your questions to him. And the videos are going to be posted later on YouTube. And if you want to receive up-to-date information about the future events, I suggest that you subscribe if you haven't to our mailing list, and otherwise you can still watch the videos on YouTube live. And so I would kindly ask you to spread the word. I think this is a great way to shorten the distance between everyone in times of isolation and today is we keep getting people logging in. 1 second. And today is a great pleasure for me to introduce Roman Lutchyn from Microsoft Station Q. And he's going to be talking about some recent developments in experimental collaborators. And well, I'll leave the room now and let Roman start with his talk.
Okay, well, first of all, thank you everyone for joining, and thanks, Adrian, for such a great initiative. It's the first time for me to give a talk on Zoom, so bear with me. I will try to, as Adrian, take questions at the end of the talk. But first, so this talk is about topological superconductivity in full shell proximitized nanowires. I'll explain what full shell means. And before I start with the talk, I wanted to thank my collaborators. So a lot of people here are my colleagues from Microsoft Quantum, from theory and simulation team. Also, I want to thank Karsten and Leonid for help with the project, as well as our experimental colleagues, Sola, Mingtang, Peter, and Charlie Mark. So the work that I'm mostly going to be talking about just appeared in Science in March of 2020. So here's the outline of my talk. And before jumping into the main subject today, I wanted to just give you an overview and start with a brief introduction. So let me start with this idea that goes back to 2010, how to realize Majorana zero energy states and topological superconductivity in proximitized nanowires. So this model Hamiltonian is very simple. It just corresponds to a semiconductor nanowire with orbit coupling. Alpha is the spin orbit coupling strength. V is Raman coupling, and delta is proximity-induced pairing. And so this model, if you just look at the normal band structure, has the following spectrum. So in the absence of the Zeeman term, we would just have two parabolas which are shifted by spin orbit coupling. But because the spin orbit coupling and Zeeman term do not commute with each other, and now there is a gap opening in the middle at k equals 0. So if the chemical potential is tuned to this point somewhere in the gap, this is a very interesting regime where essentially the system is effectively spinless. There's just two Fermi points at the opposite, at plus kf and minus kf, the spin basically is enslaved by this combination of spin orbit coupling and so now if I tune this chemical potential to the gap and I look at what pairing is doing, then one can project to the lowest subband, to the psi minus. So psi minus and psi plus are the eigenstates for this Hamiltonian. So I will throw away all the terms with psi plus and just leave the psi minus. And because of fermionic anti-commutation relations, there is a constraint on momentum dependence for the pairing term. It has to be odd on the p to minus p, and so the lowest order term is proportional to px. So, so the point is, even though we started with the S-wave superconductor, this system actually exhibits effectively p-wave superconductivity. Effectively spinless p-wave superconductivity. And we know that spinless p-wave superconductors, they support Majorana zero energy states. So what do we need to do to make this proposal work? We need to find a material with large spin orbit coupling, large G factor, and good contacts with metals. So that's the thinking back in 2010. So here's the phase diagram for this model. It's very simple. So in terms of chemical potential and Zeeman splitting, we have two phases. This is trivial phase, the light color, and that's topological phase, the purple color, dark purple color. And indeed, if you look at the local density of states, so this is density of states is a function of the length of the wire and energy. In the trivial phase, we find that within the gap, there is clean. Basically, there are no subgap states. These are above the gap excitations. Whereas if we go to topological phase, where Vx is larger than this parameter, we see states at the opposite ends of the wire at zero energy. So that's the idea. So the next thing one can ask, okay, how can we generalize this model to more subbands, more realistic conditions? Well, it turns out that multiple subbands do not change the picture qualitatively. You still find one topological band, and you still find the same qualitative picture. And so back in 2011, we proposed that concrete signature, whether this model can be realized experimentally or not, would be to look at differential conductance and see whether, as a function of magnetic field, one would find appearance of zero energy states in differential conductance. Several years later, after original proposals, this appearance in the finite magnetic field was observed by the Delft team. So here's indium antimonide, niobium titanium nitride, proximitized nanowires. Here's the IDV for this system. And you can see, as a function of magnetic field, the appearance of zero bias peaks, zero bias peak, which sticks as a function of the fields and eventually splits at very large fields. So this is well-known experiment. There are also other experiments from that era. So let me try to explain. So these are the signatures that are consistent with the model. So experimentalists did a very good job in trying to check everything they could possibly do with the system at hand. But there are also some things that started some discussion about the origin of the zero energy state, zero bias feature. So one of the things that you can see is that subgap conductance has this V shape, which is different from expected BCS-like sharp subgap conductance. And also you don't see in this picture the closing and reopening of the gap. And so it was an indication that materials need to be improved. So after this original experiment, experimentalists switched to aluminum, and the thinking behind switching to aluminum was that aluminum is the only material that does not show quasi-particle poisoning in the ground state. So there are many experiments in Coulomb blockaded islands, which I'm going to talk later in this presentation, where people measure 2E or 1E periodicity at zero field, and that's indication whether the system is poisoned by some unpaired electrons or not. And aluminum was one of the metals where we consistently see not poisoned results. So that's why that was one of the motivation. And another motivation, turns out that from materials science point of view, aluminum makes very high quality interfaces with semiconductors. So here's the first experiment from Peter Krogstrup and colleagues, where they created this very high quality epitaxial interface between indium arsenide and aluminum nanowire. And you can see that density of states is very nice. So low barrier transparency. So you see very nice, clear subgap density of states. Similar improvement was later achieved for indium antimonide, aluminum, and with similar results. So it turns out that materials quality is essential for conclusive realization of topological superconductivity, and interface properties are very important. And you can see here, for example, the comparison of two techniques. So there is a evaporated metal, so evaporated interface, and epitaxial interface, and BE interface. So in evaporated case, you can see that there is a lot of subgap conductance, whereas in epitaxial case, the subgap conductance is much lower, and this is actually the ground floor of experiment. So, so as I said, for a while, aluminum was considered to be go-to material. One of the issues with aluminum is that it has very low TC, comparably low TC. So people have tried to consider also other superconductors and try to satisfy these two constraints: increase TC, or have larger pairing gap, and also find the material which will be unpoisoned at zero magnetic field. And very recently, two experimental groups reported very interesting results for tin and lead. And you can see that in the Coulomb blockaded experiments, these materials indeed show 2E periodicity. But they also have much larger transition temperature, superconducting transition temperature. So that's very interesting development, and looking forward to seeing more results from these groups, or from these material systems. And one can ask a theoretical question: what do we gain by having this additional superconductor? So in order to answer this question, we started to use our techniques, which we've developed in the last couple of years. So on the theory front, we have been developing tools, numerical tools, which allow to simulate these proximitized nanowires and take into account geometry, electrostatic potential, and other effects, other important effects. And so here is the results. You can see, for example, that electrostatic potential, that there is accumulation layer in indium arsenide and aluminum, and this accumulation layer is very important for understanding of band structure, how many subbands are occupied, and things like that. Also, experimentally, previous phase diagrams, they were obtained for chemical potential and magnetic field. We cannot tune directly chemical potential, so we can only tune gates. And gates not only change the position of the bands, but they also change other parameters like spin-orbit coupling and tunneling between semiconductor and superconductor. So it's important to have this phase diagram in terms of observable quantities. So here's a phase diagram for this material. These are the lobes. These are topological lobes. So you can see that there are 5 subbands. You can see how different subbands require larger magnetic field, and that some subbands are more narrow, some subbands wider. You can see many details that are relevant for experiments. So what this simulation allows one to do is to take exact geometry, 3D geometry, and in this case, the wires have a hexagonal geometry, and then cover these wires with superconductor, in this case aluminum, and then basically calculate phase diagrams by putting the boundary conditions everywhere, which we know from experimental studies. We can basically calculate properties of the system and answer the question, what's the maximum topological gap that we can achieve in particular system. So here's the cut along this direction. So this is the potential profile. This potential profile, we find a few subbands occupied. And here's the main result of this study, where we show that, in the case of using reasonable parameters, and in the case of, say, lead, we can find maximum topological gap, which is of the order of several hundreds of 200s micro eV, also in the reasonable parameter regime. So that's interesting because this gap already is factor of 2 or more larger than aluminum, and it's a big change for since the gap is in the exponent, so it's a big factor overall. I wanted to say that we've developed these tools, and we are happy to collaborate with academic teams on this. Although we are Microsoft, one should not think that we are not interested in academic collaboration. So if you have some questions, please reach out. We're happy to collaborate. And finally, maybe the question that received most of attention recently in the last couple of years is the question about the origins of zero bias peaks. So here is a snapshot of a few experiments where people have measured zero bias peaks. They measured not only in the wires, but they also measured in iron-based superconductors, in 3D topological insulators, etc. And I would want to emphasize that our understanding of zero bias peaks and localized end states have improved significantly over the last couple of years. Back maybe in 2010, we believed that seeing quantized conductance might be enough. But if you look at these realistic models, there are many false positives. There are Andreev states, there are sort of partially separated Majoranas, and there are topological Majoranas. And of course, we are interested in topological Majoranas. So one of the experiments that one can do to identify and rule out these false positives is the experiment which involves non-local transport. So, so this experiment, in the simplest its form, has 3 terminals. So there is a left lead, there is right lead, and this is superconducting aluminum, which is eventually grounded. So essentially there are 3 leads, and one can calculate this conductance matrix. And this conductance matrix, in addition to local terms, probing what happens in the right and on the left, also has non-local terms. And these non-local terms tell us about bulk, and in particular become very important to understand topological phase transition. So here's, for example, results from my colleagues at Microsoft showing the phase diagram for indium antimonide aluminum nanowires, and then local conductance, and then also non-local conductance. So you can see that in local conductance, there is a mass. So there are lots of subgap states, and not all of them are topological. You can see lots of closing and reopening. And of course, with limited resolution due to temperature broadening, it's very difficult to establish which peak is topological and which one is not. But the signatures in non-local conductance are very clear. So here's the gap is closing, and then the gap is reopening. And so you can identify the exact position where the gap closed, and this is the topological Majorana peak. So non-local conductance together with correlation for the end states on both ends provides much more stringent condition and allows to rule out many false positives. And I think this is a very nice experiment, and I would even go further and say that this should be our standard moving forward for detecting and realizing topological phase. I'm going to discuss one more experiment, which is also based in non-local measurements, because these non-local experiments, they go to the core of the issue. After all, topological phase is famous for its non-local properties. So this is a not so brief overview, and I'm going to now switch to the second topic and talk about full shell nanowires, which is a new system that we discovered, which also supports topological superconductivity. So this story has an interesting beginning. So we started as two separate papers, experimental paper and a theory paper. But then when we submitted both papers to Science, the editor suggested to combine them into a single paper. And we reluctantly agreed. And I think that was the right call in retrospect, because it made us to spend even more effort to understand the data and solidified evidence for topological superconductivity in these systems. So let me just give you some history, go back to some history overview. So cylinders made out of superconductor were discussed a long time ago in the 60s. For example, this is data from a paper by Little and Parks, where they used cement and then deposited tin superconductor on top. So there is a hollow, there is nothing in the middle, and there is just superconducting cylinder. And then they pointed out that such a system shows modulation of transition temperature and critical current. And now we understand that the magnitude of this modulation depends on this parameter, vertical coherence length, and outer radius. And so depending on this parameter, which is also called R parameter, you either have weak modulations when this parameter is small, or you have very strong suppression and even intermediate phase between two lobes. So it's actually a very interesting story in this context. What happens in this intermediate regime? What is the nature of this intermediate phase? But I'm not going to go there. I want to focus more on effect of semiconductor in the middle. So when we got involved, experimentalists showed that this modulation in the presence of semiconducting core has additional effect in tunneling spectroscopy. And so when you look at zero flux, where there is very clean subgap density of states, and then you look at one flux quantum, which essentially corresponds to the superconducting wave function having a winding number equal to 1. We see appearance of low energy state, very close to zero bias. And so the question was whether this state is just some Caroli-Dejean matricon state that for some reason is very low in energy, or whether this state actually has some interesting topological origin. So in order to answer this question, we constructed a model, and we call this thin cylinder model. So as I said, and also based on some data from ARPAS, we know that there is some accumulation at the interface of indium arsenide and aluminum. And so the electrostatic profile inside of this cylinder looks like this. Because of this inversion symmetry breaking, local inversion symmetry breaking, we also expect to have a large spin-orbit coupling, local spin-orbit coupling at this interface. And for all the practical purposes, because the fields that we are interested in are very small, the order of less than 100 millitesla, we are not going to be taking into account Zeeman effect and just focus on model with, neglecting this this contribution. So here's the Hamiltonian for semiconductor. Very simple radial spin-orbit coupling, a parabolic dispersion, and also BGG Hamiltonian with proximity-induced pairing term, which has information about the winding of the phase. So using the cylindrical symmetry, one can expand this Hamiltonian in cylindrical coordinates. So here's the kinetic energy, spin-orbit coupling, and again, pairing term. N is the winding number. Alpha is the strength of spin-orbit coupling. So this Hamiltonian looks pretty messy, but there is one observation that simplifies the problem a lot. And this observation is that there is a symmetry in the problem. There is a generalized angular momentum operator which commutes with this Hamiltonian. This generalized angular momentum operator, it's a sum from angular momentum, spin angular momentum, and also angular momentum in Nambu space. So N is the winding and tau Z is matrix in Nambu space. And because of constraint on the boundary conditions, we find that this eigenvalue corresponding to this angular momentum has either integer values where N winding is odd, or half integer where N is even. So one can see then that for N equal odd, there is something special happening, that there is this zero MJ sector which transforms into itself under particle hole symmetry. So particle hole symmetry acting on a state with MJ goes to minus MJ, and therefore with MJ equal to 0, it goes to itself. So MJ equals 0 sector is very special. So let's focus on this sector more closely. So let's also simplify the radial part and consider that we have a thin shell, thin cylinder. So in essence, we will just consider a single state, single radial mode in the system. And then this Hamiltonian really simplifies, and it actually goes back, maps to the previous nanowire model. So you can see that here's the radial induced, orbital field induced Zeeman term. This is the spin-orbit coupling, which, by the way, does not average after this transformation to 0, but actually gives you finite component. All right, so as I was saying, that this model, when projected, actually looks very similar to the half-shell model that I explained before, and therefore immediately you can see that there is possibility of topological phases here. So that's the key idea here, and now we're gonna investigate this in more detail. So in this thin cylinder model, we can calculate the phase diagram and confirm, and by the way, we can calculate topological invariant and confirm precisely where the phase boundary is and what's the gap. And so here are the points along this line representing states on the left. This is closing of the gap at P equals 0, PZ equals 0. And then this is in the topological phase. So indeed, this model predicts that there is a topological phase. There is possibility of topological superconductivity here. Now, if you look at the broader phase diagram, one can see that there is just MJ equal to 0 sector, and all other sectors are either gapless or trivial in this case. which was rather unfortunate, and we were quite surprised by that. But then we realized that a lot of these basically gaplessness in these phases, it comes from this rotational symmetry of the cylindrical model, and realized the precise reason why the gap is closing, because states with different angular momentum, they do not hybridize with each other. The angular momentum is conserved, and therefore you know, some other higher energy modes that are closing the gap. So in order to study this effect of angular symmetry breaking, and by the way, you know, realistic wires, experimental wires, they have hexagonal symmetry, so they don't have cylindrical symmetry. We decided to add some modulations to test this hypothesis. So we added a spin orbit coupling, which is now angular dependent of this form. And then we saw that actually things looking much better. So these crossing points for states with different angular momentum, they reopened as shown here. And this is the complete phase diagram with these additional terms for this system. So it's nice because then you don't have to really fine tune chemical potential. You can actually work, and spin orbit coupling, you can actually work in much larger phase space. So, okay, so this was the result. And of course, in order to understand experimental system better, we performed realistic simulations where we just numerically take into account geometry, run self-consistent Poisson-Schrödinger, and then take into account very important effects for quantitative understanding of experimental data. So here's the phase diagram as a function of spin orbit coupling and band offset. And by the way, ARPA's data tells us that the band offset is very large. It's of the order of several hundred MeV. So here, for example, as you can see, as we are increasing band offset, the gap, so here's the magnitude of the gap is increasing, and also coherence length in topological regime becomes smaller. So this is good news, because that's where the experimental, that's the relevant experimental regime. And so one can actually perform this calculation, focus on one of these points, so this is the point, and perform these calculations for finite length systems. So here's local density of states. This is energy, this is position along the wire. And one can see the appearance of localized end states in the system. So this is something I want to emphasize, and that's the difference between just Caroli-de Gennes matricon states. So if we have say, a flux line in a superconductor, and you have, you don't have spin orbit coupling, then there is no way the motion in, say, radial coordinates and z coordinates decouples, and there is no way to get localized states in in z directions. You will get quantized states in sort of radial direction, but it's going to be basically a gapless mode in the along the direction of the wire. So that's an interesting effect of spin orbit coupling, that it couples radial and longitudinal directions and leads to these localized end states. And you can see here's the spectrum in the middle of the wire, so the system is completely gapped. And this is the spectrum at the ends of the wire, and there is appearance of these localized zero energy states. These are topological states. Now for comparison, these are theoretical results. This is the experimental data. And by the way, when I say theoretical results, numerical results, the parameters that we enter into the system are like band offset, dimensions of the wire, the value of spin orbit coupling, which we know roughly from weak localization measurements. So we don't fit these two curves to each other. This is just what comes out from simulations. Okay, so that's nice. That gives us confidence that these zero energy states might be of topological origin. So what do we see in transport? So we can consider the geometry that was used in experiment. This is full shell wire coupled with to some gold contacts and backgate, and then we can calculate spectroscopy. So this is the IDV, a cut along this direction in tunneling conductance, differential conductance. So you see the zero energy states, and you see some excited states. These are Caroli-Dejean-Matricon states that correspond to some excited states. And then eventually there is a gap. Now, just again, to compare with experiments, so here's experiment, you see zero bias feature, and then there are some subgap states also around. And by the way, this is how the spectrum looks like as a function of this backgate. So backgate does not affect what's going on inside of full shell wire, because superconductor screens the effect of the gate, but it mainly controls the coupling. So mainly changes tunneling between the systems. So so that's also nice. So we see qualitative and quantitative similarity. And so the final experiment that convinced us in favor of this interpretation is the experiment that involves Coulomb blockade effect. So all the previous data that I presented was done when the superconductor was grounded, or effectively this contact was completely open. So you know, there is no charging energy in this island. But one can close this contact over here and consider a floating mesoscopic island with a semiconducting part. So that's what happened. That's what was used in experiment. And then phenomenology is the following. So at say zero field, and again, this is the data. These are slides and proposals from the earlier works by Liang Fu, and also experimental work by Albrecht and collaborators for half shell nanowires, but the idea also applies for full shell nanowires. So the idea is, as a function of magnetic field, that one transitions from the regime where the transport is 2E. So in this particular case, corresponding to blue curves, you see that the ground state cycles only through the even parabolas. So this is ground state as a function of gate voltage, and we have a charging energy on the island. And then as we are decreasing the gap, at some point, pairing gap becomes smaller than charging energy. And then the system cycles through from even to odd, then even to odd. But the spectrum is still 2E periodic, because this is periodicity. So this is still non-topological phase, but the ground state can be in odd state because charging energy is large. But then finally, in topological case, we find a new picture where we go from even to odd, but actually periodicity of ground state energy as a function of gate voltage, dimensionless gate voltage, changes from 2E to 1E. And that's the state where you have, exactly at zero energy topological zero energy state. So this is the picture that we are looking for. If we have some small deviation, small splitting energy in the ground state, then the positions for the peaks, for the odd state and even state, they will be shifted relative to each other by this small tiny amount. And by looking at the scaling of this small tiny splitting as a function of length of the wire, one essentially is probing non-local property of the system. One is probing how the ground state degeneracy is lifted as a function of length of the wire. And that's a key quantity that we want to understand to to establish whether we have some ordinary states that would disperse with some 1 over L type spectrum, or we have these exponentially localized modes that will be that will depend exponentially on length. Now a little bit of theory. So the theory is very simple in this case, because in this topological regime, one can project the system to this low energy subspace and then calculate transport. This model maps essentially to some resonant level model in the absence of the splitting energy. We know the answers for this resonant level model, and they're given by these formulas. And then, as I said, the splitting energy will shift even in odd peaks by small amount. This model is a toy level model, so one could question the applicability of this toy level model. But we recently did analysis using a different model, more microscopic model using bosonization, and we found a similar picture in this tunneling Hamiltonian. So we think that this picture holds in this case too. Okay, so back to full shell. So this is what experimentalists managed to do. They took a very long full shell wire, and then they created a lot of different segments of different lengths. So they etched aluminum shell in these regions and created these islands of different lengths. So it's nominally the same wire. It's just they made breaks between different islands, and then they had contacts, and so they could run currents, you know, in this region, in this region, in this region, and so on and so forth. And this is what you see as a function of gate. And remember, the gate controls the couplings between the source and drain, and full shell wire, and as a function of magnetic flux. So you see that at zero flux or zero field, the spacing is 2e periodic, and then when we have single flux quantum, it becomes very close to 1e periodic. And so this difference between even and odd spacings is plotted here, and you can see obviously this big difference here, but it's a very small difference, much smaller difference in the case of phi naught, 1 flux quantum. So one is tracing essentially these points, the positions where the nature of the ground state is changing. So then they repeated this experiment. So this was 210 nanometers. Now this is 420 nanometers. Now 800 nanometers, and so on. They repeated this experiment, and they saw a qualitatively similar picture that there is a 2e periodicity. Then there is basically 1e periodicity at flux equal to 0. And so then this residual splitting energy can be plotted as a function of the length, assuming that the wire has the same velocity in different segments, because it was nominally the same wire. One can plot and fit the data and show that the fit is very close to being exponential, with the topological coherence lengths of the order of 200 nanometers, which actually are very close to what we find numerically. So, okay, one can say, well, how do you know that this is the only fit that would satisfy that would explain the data? So again, this is a larger picture. This is log linear plot, and this is the line. But now one can use some other models, which basically have either 1 over L or 1 over L squared dependence of the splitting energy, and see whether these other models can explain the data. And based on this analysis, we find that those other models, 1 over L definitely does not explain the data. 1 over L squared is closer, but still is worse than the exponential fit. So this provides additional signature that we're dealing with topological superconductivity here, because we see a state at zero energy, and also the splitting energy, which is, you know, a signature of Majorana's, depends in exponential fashion, seems to be dependent in exponential fashion on the system length. So that brings me to the summary. I talked today about half-shell nanowires and also a new system, full-shell nanowires. So, and how do we compare those two? So here's a summary. So tuning with a gate in B field is required for half-shell wires. The gate would not do much for full-shell because there is superconductor that screens. So we can only have tuning with B field. However, the values for the B field are much smaller. The necessary values for B field are much smaller than in the case of half-shell wires. So basically, the nature of the effect of magnetic field is completely different. It's an orbital effect. So that's a big difference. And we know that magnetic field eventually kills superconductors, so it's good to work with low magnetic field regime. Half-shell wires require large spin-orbit coupling and large G factor, whereas G factor is not really important for full-shell wires. So everything comes from spin-orbit coupling and orbital effect. So that potentially expands the landscape of materials that we can use to drive the system in topological phase. And finally, another important consideration, so we're dealing with class D superconductors, and in class D superconductors, surface disorder and homogeneity, especially coming from the charge, from electrostatic environment, they are dangerous, and they tend to suppress topological phase. So in this case, superconducting shell protects from this charge surface disorder and screens them. So there is an important advantage. So what's next? I think we have two semiconductor platforms, and would be, I think I'm looking forward to these next steps. And just to give some motivation, I think important thing would be as next to probe topological ground state degeneracy. So when I talked about Majorana islands before, these Coulomb blockaded islands, these islands had only one topological segment. But if you have several wires coupled together by a superconductor, so creating one island, Coulomb blockaded island with multiple pairs of Majorana wires, there is a new system which will essentially have ground state degeneracy even in the presence of large charging energy. And this system is very interesting. This non-local ground state degeneracy behaves as essentially some kind of spin, and there are lots of effects similar to Kondo physics that appear in this system, and even this system, this phenomenon is called topological Kondo effect. I think it's very interesting, and there are signatures in ground state dependence on gate voltage, so charging, basically in charging energy, as well as non-local transport. I also think would be interesting to probe these interferometers, so have Majorana wires coupled together, say, and put some flux quantum. Then there are interesting predictions how these interferometers would behave in magnetic field, and how the signal will depend on fermion parity in these islands. Well, and finally, I think it would be very interesting to probe the core of one of the most intriguing signature of these topological superconductors, such as non-abelian braiding statistics, and manipulate information, so form topological qubits, and so on and so forth. So so that's my summary and outlook, and I want to conclude this talk by a famous quote from Phil Anderson, said that Mo is different. And indeed, if you look at all these materials independently, such as S-wave, superconductor, just conventional semiconductor, magnetic field, each of them are very simple and well-studied materials, well-studied effects. But if you combine them together, then you can realize very interesting new physics with deep and far-reaching consequences. So I'll stop here and thank you for attention.
All right, thank you, Roman, for a very nice talk. And now I'm going to open the session for questions from the audience. So if you want to ask a question, please raise your hand. You can do that from the chat, and you can ask the speaker directly, or you can just post your question on the chat, and I will read it from there.
So Adrian, I don't see the questions, so I'll rely on you to monitor.
All right. All right, I'm going to read one question from the chat window. EBPH1 is asking a few questions. One is, what kind of software do you use to simulate the devices and to determine the phase diagrams? How do you determine the parameters in your model?
So we have Microsoft software, which was developed by theory and simulation team in collaboration with other teams. We use that software. But it is essentially Poisson-Schrödinger code, which has a lot of capabilities to calculate phase diagram and transport properties of the system. Mm-hmm. And parameters, that's a good point. So we ask our experimental colleagues to do specific experiments to determine these parameters. For example, the value of band offset was studied using ARPES. There are also experiments running STM to understand what happens at the interface. The value of spin orbit coupling, we use Vicant localization measurements to extract this parameter. So there are dedicated experiments that we use to extract parameters.
All right. There's a question by Ruben Sloane from Spain. Please, Ruben, go ahead. Sorry.
Yep. Can you hear me?
Yep.
Okay, thank you, Roman, for this nice presentation. So I was curious about what's happening in the second law, because it seems from the experiment that there is one periodic and there is also a zero IS peak. Do you expect the second law to be topological?
Good question, Ruben. So because we've broken, so I had sort of two stories. I had a story with this angular momentum symmetry, and the story was broken angular momentum symmetry. So if the symmetry is preserved, then the answer is that, you know, second lobe is trivial. However, if hexagonal shape introduces very strong perturbation, then this MJ quantum number is not a good quantum number. Mm-hmm. So therefore, in the absence of this quantum number, also the restrictions are absent, and one has to calculate topological invariant, which is still valid for a given band structure. And what we find that depending on the radius of the wire, we either have or not have topological region there. So it's very detailed questions, detail specific question, but it's possible to have if the rotational symmetry is broken strongly.
Thank you.
All right. Now we have a question from Harold Barger. Let me.
Hello. Can you hear me?
Yes.
And so I just a quick question about the tunneling spectroscopy signal. in the theory, well, both in the theory and the experiment, it was asymmetric in V bias. And I was just wondering why that's the case in this system. If you go to your slide that was called tunneling conductance.
Yeah. Yeah, so that's a good question. We have some discussion, why is it asymmetric, but experimentally this asymmetry may come from the presence of interactions.
But what about in the theory? The theory was also asymmetric.
Yeah, so I think I actually forgot. We have discussion in the paper, so I don't want to say something wrong, but we definitely considered that. One of the things that it's possible that you have a dissipation in the problem, and this dissipation basically induces breaking of the symmetry.
Mm.
There is a coupling to the leads, and so if it has non-perturbative effect, it may change it may violate this particle symmetry. But experimentally, it's coming from interaction and a coupling to the leads.
Okay, thank you.
All right, we have another question from Haining Pan, and I'm not quite sure I understand the question, but he's asking you to compare the full shell superconductors from other cases. And you mentioned that in this case, the full shell superconductor protects from charge surface disorder. And how do you rule out the possibility of trivial Andreev bound states like you have in half shell nanowires?
Yeah, so the way to rule out from trivial bound states is to, our way was to simulate different scenarios. And in the paper, we simulated different scenarios that came to mind. So what are the suspects that we considered? We considered a gapless phase, and we considered some finite system with gapless phase. So there's some splitting which is finite, and we considered some localized end states which are residing, say, at one end of the system. And in both cases, you would expect the scaling with a system length that is different from exponential. So if you look at the supplementary material of the paper, there is a whole section discussion about that. But the idea is that scaling with the system length tells you about the nature of these states. So either they are localized at one end, then the scaling will give you a constant. If they are gapless, then the finite gap will scale as 1 over L to some power, either 1 or 2. And we've checked for these scenarios.
All right, we have another question from Oleksiy Shevtsov. Sorry if I didn't pronounce it correctly. He's asking if the number of zero energy modes changes in the case of multi-band nanowires.
Well, in multi-band nanowires, there is a single band that is topological, and all the other bands are trivial. So therefore, in this picture, this one topological band gives you a zero energy state, and all the other ones, they give you some finite subgap states. They can give you some finite subgap states, but it's unlikely that they will give you robust zero energy states.
All right. If we don't have any more questions, I just want to mention one last time that we are going to host these talks weekly, every Wednesday. Some talks, especially experimental talks, will be on Mondays. We don't want to have too many talks in 1 week because we know people are busy and have other commitments, and we don't want to overwhelm their calendar. Having said this, I want to thank Roman one more time, and I hope to see you on Wednesday for Eugene Daimler's talk. Thank you very much.
Okay, thanks everyone, and see you in some later talks.